we have been discussing about this magnetic based and piezoelectric based actuators in this particular module. Now we will be discussing about this electrostatic based actuators. So as far as these electrostatic based microactuators are concerned, so an electrostatic force is created by applying a voltage across the two capacitor plates which are separated by an insulator. So example, an air gap. Thereby, an opposite charges are formed on the plate, and this potential results in an attractive force between the two electrodes. So, the ability of electrostatic actuator to generate voltage at very high frequency along with the very low inertia of the moving part of an actuator on micrometer scale allow for rapid operations. So, the basic principle underlying electrostatic actuator is Coulomb's law, acting between two electrically charged bodies, which produces a mechanical work, and consecutively in the case of an actuator, a motion that is controlled using the voltage between the two bodies. Fundamentally, an elementary electrostatic microactuator consists of two planar electrodes across which a voltage U is applied, and therefore it acts as a capacitor. Now, the force F acting between the electrode of such a system can be determined from the electrical energy Wv stored in the capacitor, like F is minus del We. If we write the capacitance as C, then we can be expressed in the following manner. In order to calculate the motor force of an electrostatic microactuator, all we need to do is to calculate the value of the capacitance C as a function of the geometric parameter of the capacitor, and then use this particular equation for understanding the behavior. So basically, if you try to look into this particular equation, the overall process depends upon this U square, and same is true for F. So it is the direction is therefore independent of the sign of U. In either cases, the forces are attractive. So we will assume that two electrodes, each of area A, are parallel and perfectly flat. Under these conditions, if x is the distance between the two electrodes, the capacitance is C equals epsilon A by x. So epsilon is the dielectric permittivity of the medium in question, and We is the epsilon A by 2x U squared. So the vector force F acting along the x-axis is F equals dou We by dou x, that is epsilon A by 2x squared U squared. Therefore, an attraction that acts between the two plates of the capacitor driven by the voltage U and increases rapidly as x decreases. Since microsystems are generally deformable and electrostatic microactuators is normally used in the manner as shown. So in this particular case, so the positive charge is fixed and the negative charge is connected to a kind of a spring kind of structure, and then the microactuator acting on a deformable elastic structure. So the rest position at U0 of the mobile electrode is x equals x naught. Now in this, like when we try to consider a vertical actuator with a parallel plate. So in this case, the motor force Fm of the actuator and the resistance force Fr are associated with the stiffness K of the structure being pulled by the mobile electrode are Fm equals U square and Fr. In equilibrium, these two forces must be equal, that is Fr and Fm should be equal. Given their dependence on x, these forces can be varied, and the influence of these forces can be studied through this equation. That is, when we try to observe the plot of Fr and Fm for the fixed U, so this is a kind of observations which is observed. However, when we try to see the characteristics here, slowly the U is getting increased. When we try to look into the vertical actuator with a parallel plate, there are therefore two equilibrium points. So one point is called as P1 and the other point is called as P2. P1 corresponds to the stable equilibrium point and P2 corresponds to the unstable equilibrium point. So, beyond the position of P2, the mobile electrode sticks to the fixed electrode. In such case, to avoid short circuit, it is useful to deposit a very thin insulating layer on the electrodes. So, when we try to consider the limit for the use of such an actuator, it is then defined by the case where as U increases, a situation is reached where P1 equals P2. The available controllable range of the actuator is therefore X0 X1. So, for the calculation of X1, the following systems needs to be solved, where we are considering one is a force which comes equal and the other one is a gradient which exists equal. So, it can be easily shown that X1 equals 2 by 3 X0, which then gives a controllable range of X0 minus X1 of the actuator as X0 by 3. This result is remarkable and it is independent of the actuator and the stiffness of the structure that is acting on it. Now, let us consider the voltage driving the actuator can be varied between 0 and its corresponding position let us consider as X0 of the mobile electrode, and U1 corresponds to the position of X1 of the mobile electrode, and when we try to equate it, this is a kind of a fundamental equation which exists. This voltage is called as pull-in voltage. This pull-in voltage plays a vital role with reference to actuation of these structures which has a kind of which works on the domain of an electrostatic behavior. This can also be nomenclated as U pull-in. Consider the example of a capacitor in a vacuum whose electrode area is 100 cross 100 micrometer square with an initial inter-electrode gap of x equals 3 micrometer. That is acting on the microstructure of stiffness K, which is equal to 2 Newton per meter, which is corresponding to the stiffness of a cantilever made of a silicon of dimension 500 into 50 into 5 micrometer cube. So, the travel of the actuator is 1 micron for a voltage between 0 and a pull-in voltage of around 13.4 volts. So, ideally this will give us a clarity in such a way that what will be the operating voltage and how much is the displacement which is expected when there is an operation voltage is exhibited on this particular system. Now, when the pull-in voltage is reached, the mobile electrode is brought into contact with a fixed electrode, or rather it is separated by the thickness of the insulating layer. So, in this situation, we treat the thickness Ti of the insulator as negligible compared to X0, and the attractive force is F equals K X0 minus Ti, which we can approximately term it as K X0. If voltage is reduced to below U pull-in, then Fm can be reduced until the situation where Fm is less than Fr, where it is reached. So, if we assume the pull-off force, the adhesive force between the two electrodes is negligible. This will result in separation of the mobile and the fixed electrodes. So, the threshold voltage that produces this separation, known as a pull-out voltage, which we call it as a U pull-out, is in such that, like when we try to integrate it, so permittivity area U pull-out will come into the picture, and appropriately U pull-out can be equated with this generalized equation based on our requirement. Now, when we try to look into the overall performance of such kind of electrostatic actuator, so we are trying to plot a graph with reference to the U pull-out and U pull-in, and then there is a kind of a displacement which exists. So, initially there is a controllable stroke is there. With reference to pull-in, there is a sudden drawback in the there is a sudden dip in the x, and then because of the contact again it is established and again it is moving towards pull out. So, this cycle will continue for the entire actuation process. So, returning to the same example used earlier and considering the insulating layer that is 100 nanometer thick, we can observe that U pull out is close to around 1.16 volts. Under these conditions, the full range of travel of the mobile electrode can be represented in terms of an hysteresis curve as shown over here. This diagram shows the controllable range, but also shows that it is possible to control the actuator in an all or nothing manner by driving the pull in and pull out cycle of the actuator. This principle is, for example, used in a scratch drive actuator, which we will be discussing in the upcoming slides. Now, let us consider one more configuration, that is a lateral actuator with a parallel plate. So, this actuator consists of two parallel plate electrode. The mobile electrode undergoes a lateral displacement with no vertical travel permitted. In this case, under the condition between -1 less than y1, in order to ensure there is always some overlap between the electrodes and the capacitance of the effective capacitor, this produce the stored electrical energy are respectively. So, these are the equations which basically takes care of the effective capacitor and the stored electrical energy. So, the force vector F produced has a strength which is represented by this concerned equation. Now, it can be seen that remarkably this force is independent of the current lateral position y of the mobile robot. That is, if u is constant, this force remains fairly constant throughout the travel of the actuator. Consequently, the stability consideration that apply to the vertical actuator are not relevant here. As in the case of a vertical actuator, the force produced is an attractive one. For the lateral actuator, this maximization of the capacitance will tend to draw the two electrodes on top of each other. This principle of maximization of capacitance can be used as a simple and intuitive way of understanding the motion of an electrostatic actuator. If y changes sign, the driving force also changes sign. Thus, the actuator works in both the directions of the displacement of the mobile electrode. Now, so these are some kind of configurations which are there to show the overall working capability as well as the functionality of this electrostatic actuators. Now, let us see some of the electrostatic actuators which are being used for micro robotic application. So, this actuator is called as a scratch drive actuator. If we try to look into the overall configuration of it, so it has an insulator, then there is an electrode which is available, and then we have a kind of a biasing capability into it in order to generate the electrostatic charge in this. So, as far as this scratch drive actuators are concerned, these scratch drive actuators were proposed by Akiyama and Shono in 1993. The principle of these devices are reported over here. One of the electrode is formed from a flexible plate and a foot. So, the two electrodes are separated by, so this is the flexible plate and the foot. The two electrodes are separated by a thin insulating layer. When the whole micro machine structure is commonly made of polysilicon, and when a voltage is applied between the two electrodes, the attractive force field produced between them implies if it is large enough that a part of a flexible electrode will stick on to the other electrode, meaning the foot will be slide forward. Now, so the actuator, now before going into this, let us see some configurations of the different types of electrostatic actuators which are being established for micro robotic applications. So, before going into this, let us see some Mechanism of these electrostatic actuators. So, or we can also say the different operation mode of this electrostatic actuators. Actuators. So ideally we have an attractive force and repulsive force in place. Let us take a simple by considering the various repulsive actuator, the attractive electrodes and the repulsive electrodes are appropriately taken up into consideration. So when we try to look into the modes of this particular electrostatic actuator, these modes are classified into two. One is called as a attractive mode, the other one is called as a repulsive mode. So let us consider the first configuration, which is a levitation of a comb drive actuator. So the configuration looks something like this. This is called as SE, AC, AE and AE. AE is called the attracting electrode, SE is called as a suppressing electrode, and AC is called as a actuated electrode. So in this particular configuration, if you see, so this is a kind of configuration which is used for a comb drive mechanism. So there is a suppressing actuator is there, and this is a kind of a and the attractive force acting between the charge, which causes a displacement by decreasing the gap. Okay, so here, so we will be having the force Fu, Fd, Fr and Fl. So these actuated electrodes will be available, and Se is used as a suppressing electrode, and then Ae is used as a attracting electrode. So the system, the actuating electrode will move between these two attractive electrodes, and it will not have any impact on the suppressive electrode. Just on the suppressive electrode it will try to stick onto the surface. Now the second configuration is called as a in plane repulsive actuator. Here we have AE, AC and AC. The force which are exerted in all the four directions, FL, FU, FR and FP. Now there is one more configuration which is called as out of plane repulsive actuator. So the configuration looks something like this: AC, AE, AC and AE. So this is a kind of configuration which is used for movement. FD, FR, FU and FL. And the last configuration is called as a three-layered repulsive actuator, which can be represented as AC, SC, AE. In the AC we have FR, FL, FU and FD. So these are the different configurations in the case of electrostatic actuator is concerned, and then these are the different electrodes which are participating towards such kind of configurations. So appropriately these configurations can be deployed for different micro robotic related applications. Let us see some of the types of electrostatic actuators which are being used for micro robotic applications. So one we had already seen is a kind of a scratch drive. Let us talk about the multiple degrees of freedom electrostatic actuator. So in this particular case we have a frame. So in this frame there is an anchor, so this anchor is connected with a serpentile kind of structure, and in order to take care of this actuation, so there is an actuation gate vertical actuation gate lateral right, and this is an actuation gate, lateral left, and then there are interdigitated shafts are there, and stationary holders. So as far as in this particular change is concerned, so this is mainly meant for a kind of a multi-directional degrees of freedom. So multi degrees of freedom with, so that we can use it for for anchoring or kind of like manipulating the beam based on our requirement. In certain cases we can also have a kind of a manipulating needle which can be used for handling and jobs. Next, we can also talk about there is one more configuration is there, which is called as perforated intermediate electrode based system. So as far as in this perforated intermediate electrode is concerned, there is a drive electrode, then there is a perforated electrodes, then we have the insulators, this is the drive electrode, and these are kind of perforated intermediate electrodes. And then there are MEMS device which exist. Based on the MEMS device appropriately, like we can have a kind of an intermittent actuation which can be expected over here. So apart from that, there is also a configuration called as bending plate actuator configuration. So as far as in this bending plate actuator configuration is concerned, length L, this is a flexible cantilever, and there is a kind of structure which exists, and then there is a rotor spring arrangement. So what happens is, when there is an actuation is there, this moves in this direction and it is retracted back in this direction. So such kind of actuators are used for a kind of a micro manipulation capability. And then of course, as far as electrostatic charge is concerned, comb drive actuators are considered to be a kind of potential configured actuators. So there are wide varieties of configuration of comb drive actuators are there. Now there is also a kind of a scratch drive actuator. So, as far as this scratch drive actuators is concerned, there is a kind of a different configuration which established with reference to a scratch drive actuator.